classification, there are few a few key models that are used. One of them is logistic regression. The other one is called decision tree. So decision tree is a very different kind of model compared to logistic regression. And logistic regression, which is a variation of regression. Both regression and logistic regression, they are equations. You are trying to uh, set up an equation that will predict the outcome based on the input variables. However, decision tree is not an equation. Decision tree is a logical tree. That's why it's called a decision tree. It's a logical if-else, series of if-else statements. Okay. And based on that, we are trying to derive which class a particular observation will belong to. And the example that we are taking was whether we can predict whether a machine is going to fail or not fail. So previously we had taken what was the mean time between failure, which was a regression problem. In case of a decision tree, we took the example where whether the machine is going to fail or not fail. Though I think I have mentioned in the last class that actually a classification problem, any classification problem in a way is also a regression problem, because regression problem, the output of a classification problem is a continuous value, which is a probability between 0 to 1, whether a particular observation belongs to a particular class or not. And we put a cutoff value. Usually the cutoff value of probability is 0.5. And if the probability is more than 0.5, we categorize the observation to belong to one particular class. And if the probability is less than 0.5, we categorize it to be belonging to the other class. So essentially, the output of a classification problem is also a continuous value, except the fact that the continuous value is a probability, and hence it is between 0 to 1, and not any value like what we saw in mean time between failure. However, the outcome of a classification problem is not exactly a class. It's not that the outcome is telling you which class the observation belongs to. It is just giving you the probability that which class it might belong to. And then we externally put a cutoff probability, and we say that if the probability is more than this value, then it will belong to a particular class, and if it is less than a particular value, it will belong to the other class. That's the difference. Okay. So that's why we say that the classification problem is essentially a regression problem. Okay, there's no fundamental difference. However, when we talk about the two models, the decision tree and the regression model, whether it's linear regression or logistic regression, there is a fundamental difference. Okay. And the fundamental difference is that in a linear regression, this is an equation, whereas in a decision tree is not an equation, it is an if-else statement. Okay. And we'll see there are certain cases where decision tree works well, and some other cases where decision tree doesn't work well. And the other important thing is that decision tree obviously is not very good in predicting a continuous value. Okay, because we can understand a decision tree is a logical if else. If certain thing happens, then it will belong to a particular class. Doesn't happen, it will belong to the other class. So it's not very good. It can be used, but it's not very good in. Typically, it is not used for regression problem. It is primarily used for a classification problem. So let us take a very simple example and understand how decision tree works. Okay. I just take this example, and then we'll take the actual data and work on it. While I'm opening the nine, just a quick confirmation. I think when I was there in Bangalore, some of you were saying that you could not install nine because certain approvals are required. Make sure that you get those approvals and install nine, because you will after probably after the your midterm is over, I will give you the uh, I'll give you the project, okay? And you need to ensure that uh, the group projects are completed. You need to form your groups, and in the group project, you would require nine. Okay? So make sure that you have nine in your install. Okay. So I'll, of course, announce the group projects, but this is just a heads up so that any approval that is required, you can take it well in advance. Just give me a second, a little bit of time to get open. Now opening the PPT is giving a little bit of problem for me. Sorry, I got the somehow the when I tried to open PowerPoint, it crashed. Are you able to hear me? Yes.
Yes.
Okay. Okay. So let us understand what exactly decision tree does with a simple example. Let us assume that we want. Are you able to see my blank PPT?
Yes.
Yeah. Let us assume that we intend to predict an app that a user is likely to use. So it's a classification problem because I want to predict what app a user will use. Okay. And we have a very simple data set where we have gender and we have age and we have the app. We have past data about the app that a particular person of a particular gender and age is using. Okay. And let's say we have these observations where we have, let's say, the first observation is a female and the age is, let's say, 15 years. And the app that is being used is, let's say, Pokemon Go. And the second one is a female. The
Professor, you're
age,
writing on the white sheet?
yeah, I'm writing. Are you not able to see this?
No, only blank sheet is there.
Oh, I don't know why this is happening. One second. Are you able to see something I've written?
Yes.
Now I'm writing again something. Are you able to see that? So the next one is a female, 25, and the female
You're
is
able to see now.
using, okay, WhatsApp. Yeah. Okay. Yeah. Okay. So we have two observation. One is a female who is 15 years, and the app that is the female is using is Pokemon Go. We have another female whose age is 25 years, and the app that the female is using is a WhatsApp. Okay. Then let's say we have a male. Somehow the PowerPoint is. Male, are you able to see I'm writing something?
Yes.
Okay. So there's a male of 32 years and the male is using Snapchat uh, app. And there's a female of 40 years and the female is using WhatsApp. And then we have another male who is 12 years and using Pokemon Go, and another male of 14 years is using Pokemon Go. Okay. So is all the data set clear?
Yes.
So yeah. So here, unlike a logistic regression where we were trying to build an equation. So if it is a logistic regression, what we would have done if we have to predict what app uh, a particular person of a particular gender and age will use, what would we we would have done? If we had to use logistic regression. First difference you would have noticed that it is a multi-class classification. In logistic regression, we have done binary classification, 2 classes. But this one is a multi-class classification. Okay, it can be done in logistic regression also, but it's slightly complicated. The second thing is that one of the features, gender, is a categorical value, whereas age is a numeric value. So you know that in logistic regression, we have to convert a categorical value into a numerical value in regression as well as logistic regression. So we had to do one hot encoding to convert gender. We have to basically have 2 different genders, male and female, and use 1 and 0 against each of these columns. But here we are not going to do that. Here we are going to make an if-else kind of a statement. So we can start with gender and we can say that if gender is female, what happens? And if gender is male, what happens? It's easier to have an if-else statement on a categorical value than a continuous value like age. Because for an if-else statement, we have to have something like if this is less than this, what will happen? If this is equal to this, what will happen? Or if this is equal to something else, what will happen? If we have to put that if-else condition in age, there can be multiple if-else conditions. Because we can say if age is less than 10, what will happen? If age is greater than 10, what will happen? Or if age is less than 15, what will happen? If age is greater than 15, what will happen? If age is less than 20, what will happen? If age is more than 20, what will happen? So we don't know at what point we are going to have an if-else statement on the age. So probably gender is an easier option we have to start with an if-else statement. Is everybody clear with the concept? Yes or no?
Yes.
Okay. So we start with a kind of a decision tree, and that's why it's called a tree, where you say gender. If it is male, what happens? And if it's female, what happens? And we have 3 different types of apps: Pokemon Go, WhatsApp, and Snapchat. Now, if the gender is male, how many users are using Pokemon Go? Can anybody quickly count? Because the data set is small, we can easily count.
2.
2. Right? So we have male, this one and this one. If the gender is male, how many people are using WhatsApp?
None.
None. And how many people are using Snapchat?
1.
Is female, how many are using Pokemon Go?
1.
How many are using WhatsApp?
1. 2. 2. Sorry.
2. And how many are using Snapchat? See.
0.
Now, do you think that I can predict just from a common sense? I'm not going into any mathematical calculation right now. We will talk about the mathematical calculation. Do you think from a common sense or from a just logical perspective, classifying or having an if-else statement on gender will help me to predict whether a user, the next user coming on board, uh, which app the user is going to use?
No,
No. Why not?
because there are multiple possibilities.
Because there are multiple possibilities. If a user is male, I cannot, if let's say if a user was male, if the data was like this, that if the user was male, all the users were using Pokemon Go, and now nobody is using WhatsApp and nobody is using Snapchat, I could have predicted with 100% confidence that if somebody is male, definitely that person will use Pokemon. But that is not the case here. 67% are using Pokemon Go and 33% are using Snapchat. And hence, I'm not sure. I'm not sure because the distribution of the observations where the gender is made is disorderly. Same is when the gender is female. Both these distributions are disorderly. Other way of defining disorderly is chaotic. If this was less chaotic, then I could have concluded easily what app the user will be using. This disorderly or chaoticness of the distribution is measured by something called entropy. We're all engineers, or most of us are engineers, and we have studied basic entropy in our engineering. We know entropy is a measure of chaos or disorderliness. Higher the entropy, higher is the disorderliness. And in this context, higher the disorderliness or higher the chaos, lesser are my chances to predict accurately what class an observation will belong. So what will be my objective? If I have to predict what outcome an observation will have, what will be my objective?
To reduce the entropy.
Reduce the entropy. So how can I reduce the entropy? So let us see if I can take, there are two ways. One is that can I take another feature instead of gender? And the second option is to create more branches to make these branches further. So let's try the first method. Instead of gender, let us see if I break it down into age rather than gender, can I create a situation where the entropy is less, if not zero. Now here is the problem, because as I was mentioning that while gender, we can clearly identify male and female. In case of age, we don't know whether we should say, because in case of age, we have to say less than something or more than something. And we do not know less than what we should put. Now, since the data set here is small, probably with little bit of observations and little bit of iterations, we can figure out that we can look at an age less than 20 and more than 20. It's just by observation, we can probably take this as a cutoff. Obviously, we can't do this by observation or by intuition or trial and error if the data set is very large. But here the data set is very small. So with little bit of iteration and observation, we can probably take the cutoff value as less than 20 and more than 20. And let's see if we can get a better result. So if the better result means a result where the entropy is lower. So if the age is less than 20, how many people will use Pokemon Go?
3.
How many people will use WhatsApp?
0. Both are 0.
Both are 0. So we know that if we take a cutoff value less than 20, we have been able to reduce the entropy to 0. And that was our objective. Because now we can say with certainty that if somebody's age is less than 20, that user will surely use Pokemon Go and not any other app. Okay. However, what happens when the age is more than 20? When the age is more than 20, how many people are using Pokemon Go?
0.
More than 0. How many are using the WhatsApp?
2.
2. And how many are using Snapchat?
1.
So we cannot say that the entropy is equal to 0 if the age is more than 20. In other words, when the age is more than 20, while when the age is less than 20, I'm sure that they will use Pokemon Go. I am not sure what the user will use when the age is more than 20. But I don't want to leave it like that. Can I now use, so I don't need to do anything with the group where the age is less than 20. Because I've already reached the conclusion that if they're less than 20, they will use Pokemon. But I could not reach a conclusion when the age is more than 20. At this stage, can I use on this set another condition, gender? And I use, let's say, let me put it in a little different way. Let me put it here only because it will be easier to visualize. So I am putting gender here, male and female. And again, I'm saying Pokemon Go, WhatsApp, and Snapchat. Now, if the age is more than 20 and the gender is male, how many will be using Pokemon Go? We know it's 0 because, but what about WhatsApp and Snapchat? When the age is more than 20 and the gender is male,
WhatsApp is 0.
WhatsApp is 0,
Snapchat
Snapchat is 1. And when it's female, age is more than 20, WhatsApp is 2, Snapchat is 0. So now with 2 levels of, you can say, if else trees, I have been able to reach a situation where entropy is 0 in all the cases. And I have reached my desired state where I wanted to predict with 100% accuracy what app a user is going to use. This is the essence of decision tree. Very, very simple. Concept is very, very simple. Okay. Except the fact that when it is a real set of data, we cannot do this just by this kind of trial and error. Because A, the number of data will be huge. The number of features will be many. So unlike in this case where we could kind of, look at the data and probably with 1 or 2 trials, we could arrive at this decision tree, which will essentially lead to a situation where I can say with 100% confidence what app a user will use. When the data is large and when there are many features, I definitely cannot do it like this. And probably have to do multiple iterations to figure out what is the best possible tree, decision tree that will give me the desired result, and the desired result being the entropy is the lowest. At this stage, I'm saying the desired result is entropy is the lowest, but very soon we'll see that entropy equal to 0 is not exactly the desired result, in the same way that r square equal to 1 is not exactly the desired result, because that might lead to overfitment. But for the time being, assume that we want to achieve an entropy equal to 0. But we cannot do that if the data set is large and if there are many features. And that is what the machine learning algorithm will do. No great deal. The machine learning algorithm will just do the iterations for us. As humans, if we try to do the iterations, probably will take a very, very long time. It will be very, very confusing for us. The human brains are not very good at doing repetitive tasks, okay, of these types. Whereas a machine learning algorithm will look at all these options and very quickly arrive at uh, the tree, the decision tree that gives me the lowest, for the time being, the lowest possible entropy. Is this concept clear?
Yes.
Correct. Okay. So let me share a data set, and we will use this time decision tree to predict whether a machine is going to fail or not fail. Let's give it a second. Uh, Want to check one data set, we will share with you. Yeah. So again, the attachment gone. Oh, I am not able to attach document here. Yeah, I've just sent you the file. Just see if you are able to read this. Yes, are you able to read this? Download and read it.
Yes.
Okay, great. So just let us examine the data a little bit before we start doing something on it. We could have done the same thing with the previous dataset, but I chose this dataset because this dataset also has categorical values. Okay, the previous dataset did not have categorical values. It was only numeric values. So this one has both categorical values and numeric values. Okay. Here you have, you know, some ID, the product ID, which probably the machine ID. Then there's a type of machine. Probably the type of machine is indicating the criticality of the machine. Again, we don't know exactly what this meaning is because this is where the domain experts will come in to identify those features that are likely to affect the machine failures. Okay, we have been discussing this multiple times that you as domain experts would have to identify the features which are likely to lead to machine failure, because only based on that, the data related to those features will be uh, taken into considerations for building the model. That's a very, very important role that domain experts have. Okay? Because without your input as domain expert, if the technical team decides what are the features, then it's likely that some important features are missed out or some irrelevant features are taken in, and the model may not be optimal. So the starting point is always people like you, not the IT team, because you have to identify the use case. And in such kind of use cases, you have to identify the features that are likely to have an impact on the machine failure. Then those features have to be collected, the data has to be collected, and models would be built around those features. Okay. Otherwise, anybody can take any arbitrary features. Okay. So here, air temperature, process temperature, rotational speed, torque, tool wear, and machine failure. The past data, so just like regression and logistic regression, this is also a classification and decision tree is also a supervised learning where you have past data of machine failure or not failure. So essentially, you have taken data at different points of time for different machines, and you have identified at a particular point of time what were the different variables and whether at that point of time the machine failed or the machine was working. Okay. And you see that there are two values here, 0 and 1. And the assumption is that 1 means one means a failure condition and 0 means a normal condition. Okay. So this is the data set that we have, and we will apply decision tree in this case for predicting the machine failure. Interestingly, we see here that there are also at least one, and in this case two, categorical values. Okay. So with this data set, let us start building the pipeline for predicting whether a machine is going to fail or not fail. Okay. So far, fine, everybody? Correct.
Yes.
Okay, so let us go back to our 9. Again, we can do it on 9 or we can do it using Colab. So by the way, again, coming back to the project, in case some of the groups are unable to install 9 for some reason, obviously they will have to do it on Colab. Okay, but I guess many of you will be more comfortable with 9 because that gives you a clear pipeline or a pictorial uh, view of the pipeline, and hence it is better that you have 9 installed. So I'm just opening 9. I'm just reopening 9 because it had to shut down last times. Yeah. Okay, so we'll go to our folder and we'll create the workflow. Let's call it predicting. Yeah. So by now you should be familiar with at least the first step. What would be the first step?
Upload the file.
Yeah. So to read the file, I think
Read
this
the file.
file is a CSV file, correct? File that I have sent you.
Yes.
So yeah. So I have to use a CSV reader instead of an Excel reader. Pick up the file just like we did last time. No difference at this stage. Okay. Everybody got it? Do you think at this stage we need to do any transformation to this file? We need to change any data type or anything in this file?
I don't think so.
Okay. We need to, because you can see here the outcome here is machine failure. And in case of regression, the outcome can be numeric value. But in case of classification problem, we have to define the outcome as a categorical value. Because ultimately you are categorizing, it's reading wrongly 0 and 1. It is thinking that these are two numbers. But these are not numbers. Even though it's represented as a number, these are two states of the machine. We don't know which state represents what, because again, that is coming from the domain expert. But we can assume here that since the ones are relatively less in number compared to zeros, we can assume here that the zeros are the non-failure cases. That means the machine has not failed, whereas the ones are the failure cases. Usually, the number of failure cases will be less than the number of non-failure cases. But 0 and 1 are not exactly numbers. They are actually two states of the machine. So ideally, they should be categorical values and not numeric values. Always remember that in case of this classification problems, the outcome has to be a categorical value. Okay, this is true also for logistic regression, not just for decision tree. So we have to go to this transformation and we have to change this machine failure from number to a string. Everybody clear?
Where we have to go to this transformation actually?
Okay, the screen may not be visible.
Because your
So there,
screen
yeah,
is,
yeah,
yeah,
okay, got it, no problem. I'll just tell you. So you are able to go to the configure, and when you go to the configure screen, so normally the default tab is the settings tab where you read the file. On the right hand side of the settings tab, you see there's a transformation tab. Are you able to see that?
Yes.
Yeah. In the transformation tab, it will give you all the different data types. And there you will see that the data type of machine failure is integer, and that should be converted to string. In fact, if you see that UDI, which is kind of an ID of the rows, that is also being read as a number. But ideally, this is not really a number. It is also an identification of the rows. So it can also be converted, or it should also be converted to a string, but we are not doing anything here because typically we will not use this field, and we'll come to that very soon. There are a couple of fields which should not be used for the purpose of as features for the purpose of prediction. Okay. So that's why we are not doing anything with the UDI field. But machine failure is something that we will need. And hence we are, and we have to convert that to a string. Okay. So far, fine, everybody?
Yes.
Correct. Can you tell me? So we'll execute this and we will be able to read the data. Can you tell me what is the next step? So here you can see that I can read the table and there are statistics also. Let's see if there is any missing values, because if there are missing values, obviously we have to treat the missing values. But these data sets are relatively clean and you see that there are no missing values. There are 10,000, different values. And for the numeric values, it's minimum, maximum, 25% quartile, 50% quartile, all those things are given. What do you think is the next step?
Filter.
So this is, yeah, sorry, go ahead.
No, I was telling filtering we have to do. What is not
Yes,
needed.
which are the ones which are not needed? Absolutely right. Filtering. Or not just not needed. One is not needed, the other is they should not be there.
They should not be there.
So which fields should not be there as features or outcome? Outcome, of course, is one, machine failure, as features in my data set. And I must filter them.
One is UDI is not required.
UDI is not required.
Product ID.
Yes, probably product ID is also not required, though product ID has some intelligence like L, M, you can see that's a part of the product ID. But since that value of L, M has already been extracted as a type, we no longer should use the product ID. Any reason why we are not using UDI and product ID? Or we are filtering them out?
UDI is having all unique,
Yes.
I think, values for each
Yes.
row.
Right.
So that will not make any sense because that will create one more,
Okay.
I would say.
Yeah, got it. Got it. If this was not unique, let's say there are 10,000 records and let's say, let's assume type. Right now, whatever we can see, that type has only two possible values, M and L. We can check that in the statistics, how many possible values type has. Type has, let's say, three possible values. Okay, there is one more value somewhere type. Okay, if this type, instead of having three possible values, if this type had 8,000 possible values, not so that means it's not unique. Okay, but it has 8,000 out of 10,000 values. There are 8,000 different values of type. Would that should we have included that as a feature?
No, we should not use.
So what is the reason?
Reason is again, it will become too complex for the.
No, we have to give a we have at this point of time, right? We are into few courses on machine learning, not just this course. So we have to be little more technical in defining the reason. Okay, we can't just define the reason in a commonsensical way anyway. At this stage. So the technical term that is used, anybody remember that why such cases, such values should not be used? Is high cardinality. High cardinality. Note it down. Okay. Because these are the important things. As when you're building a pipeline, these are the decisions that you have to take. Again, a lot depends on the domain expert to take these decisions, not on the technical team. So high cardinality means that the number of possible values is very high as a proportion, as a percentage of the number of unique values. So what is the number of unique values? 10,000. Number of possible values for any variable is considerably high compared to the number of unique values. So in case of UDI or product ID, it is 10,000. So the ratio of number of unique values of product ID to the number of rows, the number of records, observations is equal to 100%. All of them are equal. But if there were 800 different types, then it would have been 80%. Still, we had to exclude that. So is there any thumb rule? Yes, around 30%. If I see that around 30% of my values are, or the ratio of the possible values to the total number of observation is greater than 30%, such features will be called as high cardinality features. High cardinality features will not render itself to any pattern or unlikely to render itself to pattern. Okay. So you cannot derive a pattern of machine failure from the product ID. However, if I force this to be a feature, the algorithm will assume that there is a pattern when there is no pattern. And hence the model will not be optimal. That is the reason. So it's not just where the values are unique, but also where the values are, the ratio of the number of unique values to the number of observations is relatively high. How high? Around, let's say, more than 30%. Clear? So here in this particular case, we find that UDI and product ID are the only two features or variables where this ratio of number of unique values to the total number of observations more than 30%. In fact, they're 100%, and hence they should be filtered out. So that's what we are going to do. Now, UID, by the way, is probably the primary key. Primary key means the field or the attribute that uniquely defines a row. Probably it's the primary key of each record. However, when KNIME imports the data, KNIME gives its own primary key in the form of row ID. And that is what KNIME is going to treat as primary key, because KNIME does not want to figure out whether the UDI is unique or not. So that is why whenever we are importing any data, KNIME does not depend on any specific primary key of the data unless I specify in the configuration. When you're reading the data, there is a possibility where I can specify that anything is a primary key. In that case, KNIME will take that as a primary key. But we have not specified that. And usually, we allow KNIME to give its own primary key. And that is the reason why we can exclude UDI. Up to this concept clear? Everybody?
Yes.
Correct. So we will use what kind of filter to filter out UDI and product ID? It is a
Filter.
Column filter.
Column.
Yeah,
Column.
because there can be row filter also. Okay, for example, let's say if there are missing values, and we know that the first option to treat any missing value is to remove those rows having missing value. So there can be row filter also. Okay. But here we are going to use column filter. Connect. And let's say which one we want to filter out. We want to filter out UDI. So here if you see that in the feature list, row ID is not there. But UDI is there. The reason row ID is not there is because row ID KNIME has incorporated as a primary key. KNIME knows that it is a primary key. So it will not take in any feature, but it doesn't know that for UDI. And that's why UDI you have to specifically exclude. These two we exclude and rest is fine. Execute it. And now we have the data without comments. What is the next step that we typically do? At the broad activity that we do after this step.
Box plot.
So if I have to categorize this broad set of activities, we call that exploratory data analysis.
Yeah.
Okay. So this flow is very important for all of you to understand. And this is the foundation of knowing machine learning as a subject. Since your course is about analytics, so this is something that you have to internalize, memorize, kind of. Okay. It shouldn't be that you should refer to any PPT or any book. Okay. Moment a problem comes in your mind, it will be like a picture. That what are the steps that should occur like a picture. Okay. So that is the internalization window, right? So like in your job, there are certain things that it is at the back of your palm. Okay. Okay. So moment you see this data, your experience tells you something is wrong. So that if you have to build one set of expertise in machine learning, it is that set of expertise. The moment you know a use case, I must know what are the steps that I should do. Okay. So exploratory data analysis.
Sir,
Exploratory data, yes. Please.
just before that, I actually installed KNIME a couple of days before. I'm able to follow you whatever you're doing, but I just missed out on when you added this column filter and below the values are showing. But for me, I am unable to see the values for this column filter. I don't know whether I
Yes.
have missed something or not.
So just see if you have you executed, just see if it's green.
No, it's yellow color.
Yellow color. Na? So you have to execute. You see there is a small play kind of a button on the top left, or you can right click and you can just say execute. Okay, there'll be an execute
Yeah.
button. Once you
got it.
execute, this will become green. Okay. So
Yeah, got
so
it, got
remember that any node it will give you the output once it has been executed.
Thank you. Got it.
Correct. Okay. So the purpose of EDA is to figure out whether we need to do any data cleaning or not. For example, purpose of box plot is to find out any outliers, and if you need to treat the outliers, and the purpose of various other things are there. So some of the key things that we know of course, is box plot. But before the box plot, we also want to know that what is the distribution of the status of the machine. Remember, the status of the machine is 0 and 1. I want to know how many machines in this data set of 10,000, how many are 0 and how many are 1. Now, of course, I can do it in the statistics also. Statistics also will give me the values, but a better way to visualize it is through a pie chart. So my objective first is to figure out how many zeros are there and how many ones are there. And I'll ask you the reason for this. Okay, but let us do this first. So that is one of the EDAs that we'll do. Okay. Now this is not the only set of EDAs what I'm showing. There may be more advanced set of EDAs, but if you know this, some of the key EDA activities, I think in most of the practical use cases, this is good enough. Okay. So you take pie chart. Yeah. So what we want to have a pie chart of is the machine failure. And in the machine failure, I want to find out the occurrence count. How many times 0 appears and how many times 1 appears. Okay, everybody clear up to this? Apply and execute. And it shows that you have 96.6% cases, 9661 of 10,000 values, where the value is 0. That means the machine has not failed. And you have 339 cases where the value is 1. That means the machine has failed. What is your observation about this distribution of data? That 96%, 97% cases, the machine has not failed, whatever data we have collected, and 3% case, the machine has failed. Is this data good enough to proceed, or there is some challenges with this data? First, think of it from a logical perspective, and then later on we'll think of it more from a technical perspective. Yes, anybody?
Logical perspective, the data what we have collected is showing that around 3% of the instances there is a failure possibility.
Right.
So
not possibility, these are failures. Okay.
Failures,
this
correct.
is
Failures.
past data. The actual failure has happened. Yeah.
Actual failure. So with this, I think we will be able to take this data as a for predicting for the future, maybe.
Okay.
So this can be used.
Okay. The answer is there is a challenge in using this data for building a machine learning model. This type of data is called imbalanced data set. Imbalanced data set means that one of the classes is represented or underrepresented, let me say. There are very few observations where the machine has failed compared to the observation where the machine has not failed. Now, moment we, what do you mean by underrepresentation? That means the percentage is less. Now, why is this a problem? Because when we are asking, again, from a just logical perspective without mathematics, when you're asking a model to learn, the model has to learn from both the situation, when the machine has failed versus when the machine has not failed. And it has very few instances where the machine has failed. So obviously, this opportunity to learn is very less. It's like saying that, let's say you have two chapters in your subject, and in the practice exam, you have 100 questions from one chapter and only 5 questions from another chapter to practice on. But in the examination, questions can come equally from both the chapters. So obviously you are underprepared for the questions of chapter 2, where you have only practiced 5 questions. Whereas you are kind of over prepared or more than adequately prepared for the questions of chapter 1. Same thing happens for the machine. The machine will be underprepared to predict a failure. And actually that's the problem, because you want to predict failure. You don't want to predict not failure. Right? So this type of data set is called an imbalanced data set. Again, a very, very important thing for domain experts like you. So remember that any machine learning use case that goes to your technical team must be filtered by people like you. Now, when I was in Bangalore, what I discussion with some of you made me believe that you have within your domain team, you have 1 or 2 people who are designated as data scientists, and they are supposed to be having sufficient, of course, they are domain experts and having sufficient knowledge of analytics to play that anchor or that, uh, you can say the linking role between business user and the data science team. And that's the type of knowledge that many of you should have. And more number of people you have as domain experts, lesser will be a dependence on 1 or 2 such people in your team. So ideally, a larger number of people will should become domain experts, so that they can identify these cases, these challenges, and build this prototype pipeline to figure out the feasibility of this particular uh, project before this is taken up by the data science team as a full-scale enterprise project. Because the moment we're talking about a full-scale enterprise project, we're talking about heavy investments in huge amount of data, big data, cloud, etc., model deployment, etc. So it's not a very good approach where you invest in these technologies and then figure out that in the very first place, either the use case is not established or probably the data itself was not ready to render itself into such training. That's why as domain experts, or that's why as domain people, you need to know this particular stage. Is this challenge clear, first of all? And this is a very common challenge. It's a very common challenge because on various types of scenarios, especially classification problem, because usually you want to classify or predict something that is not natural. For example, failure of a machine is not natural. You want to predict that. Let's say a credit in a different industrial context, a different industry context, credit risk. Okay, risk of customer not paying the loan is not natural. Most customers pay the loan, but few don't pay the loan, pay back the loan. Most credit card transactions are genuine transactions, but few can be fraudulent transactions. In medical domain, probably most people who are undergoing any test are healthy people, but there can be few who are detected as not healthy. So in many such cases, we have this situation of imbalanced data set, where one of the classes, and usually the class which you want to predict, that is underrepresented. Now, obviously, the question can be that what is an underrepresentation? Again, the thumb rule is that if one of the classes is represented less than 20%, then it can be said underrepresentation, and the model will not get adequately trained on those cases. Okay. Up to this clear, everybody? Concept clear?
Yes.
Now, obviously, the question would be then what do we do with this? This is what the data has come. So what do we do with this? What do you think we should do? We need to make the one cases at least 20%.
So we need to extract, get more data.
So one option is extracting more data, and just not extracting more data. We have to extract the more failure data, because if we extract more data, again, the ratio will still remain the same. Okay, because there will be less cases of failure. So we have to, by design, extract only failure data. That may not be very easy in a real scenario, because essentially you cannot engineer a failure, right? You don't want to see, we always say that in academic world, the academicians always assume that it's very easy to conduct experiments. Okay, they'll say, okay, we'll do a research and we'll take a control set, and we take a experimental set. So for academic research and certain categories of research like economics and all, it's easy. But in real industry, it's very, very hard to do experiments, because the real impact on business. I cannot say that next 1 month I'll make the machines fail and collect the data. Right? Your management will scream at you and say that, forget about all this machine learning stuff and all. Okay. I cannot, for your machine learning prediction, what will happen, work or not work, I cannot approve that, okay, machines will fail and then I'll collect the data. Okay. So you have to keep on. So if 1% of your machines are failing, or 5% of your machines, are 3% is failing, you have to collect the data for, let's say, 2 years, maybe, and filter out all the data or part of the data which are non-failure cases, and keep only the data that are failure cases. And that's how you are able to build a balanced data set. And that too, there will be challenges, because it will not be a right sampling. So it's a problem. In a real scenario, collecting such data is a challenge. And that's again where domain experts like you has to come in, that look, this is a problem that we have. How do we collect the data? Fortunately, with the advent of generative AI is actually quite good in this, where even before generative AI, this was used, but it was much more complicated to generate synthetic data. So from the patterns that you see, which will lead to a machine failure, you generate other data that are kind of simulating a scenario of machine failure. So with advanced generative AI, this generation of synthetic data has become very, very popular and has become very accurate also. So later on, if time permits, we'll see how we can generate synthetic data using generative AI. Again, that's where, as domain users, you will have a role to play. Because once you have synthetic data generated, you cannot use it just like that. You have to have human guardrails, which will check on a sample-based basis and using certain parameter whether the synthetic data that has been generated by generative AI, is it right, or the generative AI is hallucinated. As of now, we will not generate synthetic data. We'll work with this underrepresentation. But having said that, we can expect that the model that we'll get will be probably not very accurate. Okay. But for the time being, we'll live with it and we'll work with this imbalanced data set. So far, fine, everybody?
Yes.
Concept clear? Great. Okay. Some of you already mentioned box plot. Yes, that's a very important EDA. So we do a box plot. Ideally, we should do a box plot for all of the numeric variables because box plot can be done only on numeric variables. Probably let's do it only for one, maybe air temperature. See the box plot. Seems to be a pretty consistent value. So let's take something else. Works better. Toolware. So this is a box plot. So we can figure out box plot for other numeric values as well. And if there are any outliers, obviously you have to treat that. It seems that toolware doesn't have any outlier. What is the other thing that we typically do?
So through this box plot, we have to identify the outliers and
Yeah. So since we are not getting into removing the outliers, and there seems to be, even if there are outliers, there are probably not many. So probably if we're ignoring that. So apart from identifying outliers, what is the other, any other EDA that you should typically do?
missing values
No, missing
we check
values is
in the rows. Yeah.
before actually EDA. Okay, missing values is before EDA because missing value data is you can identify at the first stage itself. It's like column filter. EDA means you're exploring something. Missing value, there's nothing to explore as such. It clearly shows whether there are missing values or not missing. There's nothing to analyze as such. Whereas when you say imbalanced data set or you say box plot, outliers, you are analyzing something, right? So typically missing value is something that you do before the EDA stage. Another very important things we have done. We have done, sorry.
Scaling.
Scaling is not EDA. Okay, scaling is an activity that we do for regression. There is an action after EDA. That's a part of data preparation.
Okay. We do correlation also.
Correlation, yes. Linear correlation, yes. Just kind of internalize this, okay? Because this is the core of any machine learning. Okay, so that you don't. It's kind of, it should be there like a picture in your mind that whenever you want to do any use case, mentally you know that these are the steps. Without referring to any books, without referring to any notes, this should be coming automatically to you. Okay, so linear correlation. Why are you doing linear? What are you trying to figure out in linear correlation?
We are trying to see if the features have are related to each other, so that we can remove if any common features are there. Or
right. So linear correlation works only with correlation. This is a numeric, no, it's a metric. So linear correlation obviously works only with numeric values. It doesn't work with, so there are features here which are categorical. So linear correlation will not work on categorical values unless we decide to do a one-hot encoding. And usually we don't need a one-hot encoding in decision tree. Okay, we saw that when we are doing the simple example of gender and age. So linear correlation will work only for the numerical attributes or numerical features. And the purpose is to figure out that if features are correlated with each other. The assumption or the null hypothesis is that the features are not correlated. Again, as domain experts, you have a role. When you identify the features, you say that vibration, temperature, as per my engineering knowledge, these are the features that are likely to lead to machine failure. Based on my engineering knowledge and based on some cases also the tacit knowledge. Like a car mechanic can think of a sound. Okay. which is probably not there in manual anywhere, but a particular type of sound, the mechanic knows that there is a problem. So both your engineering scientific knowledge, documented knowledge, as well as tacit knowledge, which you have acquired over years of experience, looking at the machine, maintaining the machine, that these are the features that are going to impact my failure. Out of these features, based on my engineering knowledge, these features are relatively independent of each other. For example, the machine temperature and the ambient temperature are relatively independent of each other. Whereas the machine temperature and, let's say, vibration, there is a dependence. And the dependence can be one way or two way, both ways. For example, if the temperature increases, the vibration may not increase. Temperature may increase in various ways because of various reasons. But if the vibration increases, the temperature will definitely increase. Engineering knowledge. So you as engineers have to first kind of think of, are these features independent of each other? The null hypothesis is that they are independent of each other. Unless your data shows, so your hypothesis may be incorrect also. Okay. And you will statistically see if your hypothesis is incorrect. So when you are taking the features, your null hypothesis is that they are independent of each other. Your linear correlation will say that whether your null hypothesis can be accepted or rejected. Your null hypothesis was the ambient temperature and machine temperature are independent of each other, but the data shows that this null hypothesis must be rejected. Your assumption was incorrect. On what basis we accept or reject the null hypothesis? You know the value? We'll discuss this in regression also.
P is less than 0.05.
P value, yes. P value is less than 0.05. Of course, you can also use T value, but usually instead of T value, it is P value is a better measure. We'll not get into why it is a better measure. It's more of statistics. So P value less than 5% indicates that the null hypothesis that these two measures are independent of each other is no longer true. And then as a domain expert, you have to decide, not the data science team, that if two values are ambient temperature and machine temperature, they are highly correlated, what should be done? You as domain expert will say that, look, ambient temperature is less important, it is unlikely to have a large impact on machine failure. Let's drop ambient temperature and keep machine temperature. It's a decision you take, not the data science team. Or you can say, look, both are important. So we will create an artificial measure, which is a combination of ambient temperature and machine temperature. Let's say a product of machine temperature and ambient temperature, something like that. That kind of artificial measures is done through something called principal component analysis. Okay, principal component analysis again can be various ways. I gave a very simple example where you just make a product of that, but then you are there are other more complicated ways of doing that. Okay, so that's the purpose. Okay? So once your concept is clear, you can always catch hold of a statistician and say that, can you just do this is what the linear correlation I've got. Can you just analyze this for me? Okay. That's fine. But I must know in my head that linear correlation is required. Okay. Because otherwise, the statistician may not come and tell you that this is required. So open that. So here we will not do a linear correlation with. There's no point in doing with numeric categorical values. Also, of course, machine failure is an outcome here. Is anyway a categorical value. If it was a numeric value also, we would not have done a linear correlation, because linear correlation is always done on the features. We are trying to find out the relationship between the features and not between the feature and the outcome. Feature and outcome relationship is what the model is going to build. Okay, fine. Okay, execute. So this is the correlation matrix. So symmetric diagonal matrix, where the diagonal is 1 and for example, row 1 says what is the correlation between process temperature and air temperature? That is 0.876. The process temperature and air temperature have a high correlation. And similarly, this value is also 0.876 because process temperature and air temperature correlation is same as air temperature and process temperature. So it's a symmetric diagonal. And here you can see negative. So torque has a negative impact on process temperature. If the torque increases, the process temperature will reduce. But the question is that these values itself do not say anything, because from these values, I cannot determine what would be considered as a high correlation to say that these two features are sufficiently dependent on each other. It's just a number. I don't know whether 0.876 is high enough or 0.023 is high enough or 0.019 is high. I don't know that, but I just know a value. Okay. What would be a high correlation to warrant a treatment on the features will depend on the p-value. So air temperature, process temperature, p-value is 0. Can anybody tell me what is the meaning of this?
It means the air temperature is not dependent on the process temperature, or when the air temperature increases, process temperature does not increase. That means they are not dependent on each other.
Right. If you have to make it technically more perfect, we'll say the null hypothesis is air temperature has no impact on process temperature and vice versa. Okay. And the alternate hypothesis is air temperature has an impact on process temperature and vice versa. So, sorry, opposite. Null hypothesis is that the air temperature and the process temperature are highly correlated. Okay, opposite. Okay, so yes, just checking. Rotational speed and you can just check whether we have formulated null hypothesis correctly or not. So rotational speed and tool wear, the p-value is 0.982. That means under normal circumstances, I would accept the null hypothesis. Let's see what is the relationship between these two. Rotational speed and tool wear, right? Rotational speed and tool wear. Tool wear. This is 0. Okay, so that means the there is no correlation between rotational speed and tool work. Okay, so here our initial formulation was correct, that the null hypothesis is that there is no correlation between these two. And the alternate hypothesis is that there is a correlation. So when we say air temperature and process temperature, their p-value is less than 0.05. I am rejecting the null hypothesis that there is no correlation between air temperature and process temperature. Correct? Confusion clear? Yeah, in fact, here you can see the correlation value is also given there, not as checked over. Make sure this is very clear.
But the null hypothesis is true when my air temperature is not impacting the process temperature.
So first of all, look the other way around. P-value equal to 0 means I am rejecting the null hypothesis.
Rejecting the null hypothesis.
Okay. So here there is a correlation.
Yeah.
High correlation. So if I'm rejecting the null hypothesis, what would be my null hypothesis? Null hypothesis is that there is no correlation between air temperature and process temperature.
Yeah.
And I'm rejecting the null hypothesis. And that's why I see a high correlation. But the question is that whether this is also a high correlation. If you see that this one also is, I am rejecting the null hypothesis, but here you see the correlation value is very small. But still I'm rejecting the null hypothesis. That means I'm saying that air temperature and torque are correlated with each other. So apparently, if I don't see this p-value, it will appear that they are not correlated because this value is relatively less. That is why just looking at the correlation value, I cannot decide whether there is a high correlation or low. I have to look at
here the correlation for air temperature, for process temperature, correlation value is high, 0.876. But
yes,
still we are rejecting the null hypothesis.
So my null hypothesis is there was no correlation. I'm rejecting the null hypothesis and saying that there is a correlation value is high. On the other hand, here you see the correlation value is not as high as 0.876. Correct. But this is sorry. This is also what we are rejecting. No. Let's
take the second one. The second one.
Let's take second one. Yeah, let's take second one. Okay. So here you see the correlation value is only 0.023. So if I compare with this one and this one, it will appear that the air temperature and rotational speed are not correlated. Right?
Yeah.
But actually, here also I am rejecting the null hypothesis that they are not correlated because my p-value is less than 5%. So null hypothesis is that they are not correlated. I'm rejecting the null hypothesis because the p-value is less than 5%. And I am saying that they are correlated, even though the correlation value independently are very different of these. Concept clear?
Yes.
Right. Okay, so ideally, again, we should have worked on, let's say, either dropping some of the features or let's say doing principal component analysis. Again, for the time being, we will not do that treatment. No, that's not correct. Okay, in a real scenario, you have to do the treatment. The reason I'm not doing this is slightly complicated. Second is you don't have too many features. Let's say if you drop few features, the number of features that also you have to understand that number of features that you are left with will be very less to actually do a proper prediction. And there is also something called combination effect. Even if individually they are not, they are highly correlated, combination of them may affect something else. So Sometimes you cannot directly remove any one of the features. And that's why these iterations are required.
But sometimes in case the correlation value is almost close to 1. So we can straight
Right.
away do a column filtering and
You
remove
can straight away, yeah, you can straight away do that. However, idea is that you should always experiment. That means you should build two models, one with both the features present, another with one of the features dropped, and see which one is giving you the better accuracy. And that is why you need to do this modeling before actually you implement the project. Because when you are experimenting, your experiments have to be light. Your experiments cannot be very expensive. Otherwise, your management will not approve so many experiments. So in the beginning itself, if I invest a lot in a data lake and building a machine learning model on the cloud, etc., and then say that, look, now I want to go back and iterate. Okay. And now you want to try with both the features. Initially, you thought only one feature is sufficient. Now, for some reason, you are thinking, let me also try out with the other features, even though statistically it is saying that it's highly correlated. The management will say that the project cost is escalating. Because one moment you are putting this particular type of project in a real environment with a high volume of data, real streaming data, etc., it's a huge cost. And that is why before it goes to those days, these experiments have to be done with in this kind of tools where the cost of experiment is lower. Okay. Great. So as of now, we are not doing any treatment and we'll go ahead with this. We are go ahead with the existing data. What do you think is the next stage? Just think of logistic regression and what did you do next in logistic regression?
we have to do the scaling.
You have to do the scaling. Do you think that is required in decision tree? Think logically and answer. Do you think we need to scale all the values? A scale of 0 to 1 or whatever is the scale. Yeah, logically, what do you think? Should not be very
Logically,
difficult.
it is not required.
It's not required. Okay. Why do you think so?
Because since we are looking at classification,
No, logistic
the
regression is also
numerical
classification.
value
No,
will
no,
not.
logistic regression is also classification. So that cannot be the logic. Logistic regression also we did classification, right?
Yes.
You're right, but the reason is not that. Think a little more, you should get the reason. See, decision tree is about a logical if-else condition. If male, if female. If age less than 50, age more than 50. It is not an equation. So since it is an if-else kind of condition, it doesn't matter what is the scale of the values, isn't it? If height less than 1.5 meters or height more than 1.5. Weight less than 40 kg, weight less than 60 kg, weight more than 60 kg. How does it matter whether I represent the height and the weight in the same scale? It mattered in case of regression and logistic regression because we are trying to build an equation And we need to ensure that no feature has an undue weight on the outcome. But here it is not an equation, it's an if-else statement. Reason number one. Reason number two is anyway, some of the attributes are categorical values, like the machine type here. You cannot do a scaling or a normalization on a categorical value. You can do a scaling or normalization only on numeric value. And you already said that in this kind of decision tree situation, you don't need to convert any categorical value to a numeric value because it is again a if-else condition. In fact, it will work probably better if it's a categorical value because just we are saying if age is male or if gender is male or gender is female. Am I correct?
Yes.
Right. So remember, in decision tree, you do not need to normalize the data. This is another advantage of decision tree. So we can straight away go to, without normalization, the next step, which is, so ideally
Training
this
and
was the
testing.
EDA. Yeah, ideally this is the EDA. After the EDA, there should be data preparation, where any action that we need to take from the EDA, whether we are talking about having a more balanced data set, okay, or balanced classes, or we want to remove outliers, or you want to treat those features that have high correlation, all those things will be part of data preparation. We are ignoring that data preparation stage simply because it is a little more complicated. Okay. And usually see, as domain expert, you really don't need to know how to do those, how to how to generate synthetic data or how to do a PCA. But as domain expert, you must know what needs to be done. You need to know that, yes, I have to do some feature engineering. Okay, I have to balance the data set. Okay, I have to find out outliers. So that's where the interface with your data science team will come. So tell, okay, have you done this? Because this seems to be a imbalanced data set. So, how do we treat that? Do you want me to get more data, or do you want me to generate some synthetic data, or would you generate some synthetic data? So that is the type of discussion that should happen between you and the data science team. Okay. So we straight away go to the partitioning. Now, I'll not get into partitioning today because in sampling, the method of sampling for any classification problem is okay. I think we have done this, okay, or in the same in logistic regression. So I think we can do that quickly. What is the method of sampling that we have done in case of logistic regression compared to, and how is it different from linear regression? Anybody remembers? In linear regression or any regression for that matter, what is the sampling technique that is used?
Random.
Random sampling. In any classification technique, whether it's logistic regression or decision tree, what is the type of sampling that is used? Anybody? Stratified sampling. The whole idea is that both the samples, which we're calling as training data set and testing data set, they're nothing but samples of the population. They must have representatives of both the classes in the same proportion as in the population. Stratified sampling. Clear?
Yes.
So I think we'll close here today. We'll do the next cycle, which is because that involves how exactly addition tree will work here in our next class, which I think next Saturday we don't have class. After that, okay, right after that we'll cover this. Okay. Any questions before we close for today? Great.
My
So
question
then,
is on the project. So maybe
yes.
it is too early to ask. I am not sure.
No, not too early.
Uh,
I will of course detail out the project. Say the project will be, I'll give you a data set and you have to, and this data set obviously may not be the ones that we have worked on. And you have to build a model and nine. And typically what I ask is, because otherwise what happens is that how to differentiate between the groups. So I ask you to record, okay, record your activity. So let's say 4 of you are in a group. So you have to, you can create a Zoom account and you record the steps. You also communicate, describe the steps. Typically, like in a class I'm doing, I'm saying that these are the steps that you need to do. Similarly, you have to describe the steps. Upload the video in a YouTube channel. So you create a YouTube channel, any one of the group members, upload the video. Do not upload the video in that e-learning portal, because e-learning portal cannot accommodate such a big size of video. So you have to upload the video in a YouTube. You create a YouTube channel in your own name, upload the video, publish the video. Later on, you can unpublish it and give the copy of the link against the assignment section that is there in e-learning. Okay. That is the typical way I conduct assignments. So unlike probably many other assignments, it's not like a report or PPT files, because you already know by now that I don't believe in PPTs or learning by PPTs. So it is not going to be a PPT or something.
Last semester we had a challenge of capturing the video and sharing it with the professors because of the Bosch intellectual and then some compliance related topic.
Okay.
So maybe that we have to.
So you let me know if that is no. I really don't find a reason for this, because this is your assignments is not based on any data that is relevant to Bosch. So whatever video you're recording has nothing to do with any Bosch's intellectual property as such. Okay, it is a completely different data set, which has nothing to do with Bosch. So ideally, there should not be any logical reason for any objection. But I understand that in corporate, sometimes there are stringent rules. So if that is the case, let me know. Then we have to figure out some other ways. Okay.
Okay. Maybe the restriction would be on using the official laptops and also the names as a Bosch entity when we are discussing and doing the project.
No, that's why. Yeah, so the data set has nothing to do with Bosch. So there's no, even when you're discussing something, there's no reason why you should take the name of Bosch, for example, because the data set is completely different. Nothing to do with Bosch.
We will discuss and.
But you check that. Okay, I understand the concern. You check that and see, because then otherwise we have to figure out some other way. Because the problem with this kind of assignments is that if I just take a submission on just the 9.5, I have no way to check whether one group makes a 9.5 and everybody else just uploads the same 9.5.
Correct.
Okay, so there's no way to validate that. The other option is, I don't know if there's a second visit, but that will be little, and that's not the purpose. I think that would be incorrect, because normally when I conduct this type of courses on a in-class mode, many of these courses are in class. So there I ask the groups to do this activity in the class. So when you do in the class, obviously you can't really, still there is an option, but it's difficult to and then you can see that what each group is doing. But in online mode, I have no way to check whether one group has done it and then somebody else, some other group has just uploaded the same 9.5.
Right.
So yeah, so just good point. Just check it out. If there's an objection, then we have to see what other options we have.
So the
Okay.
expectation is that when we are preparing the model, that we record that as a
Right.
Zoom or a Teams
Right.
discussion, and then we have to do it and then upload it into YouTube channel.
Right. Absolutely. Yeah, because that's the way to ensure that the group is doing the work and not anybody else is doing it.
Okay.
Great. Okay. Any other questions? Okay,
No, sir.
great. So I see. I think next week we don't have class. Like 4th, we don't have class, and then
Yes.
we meet after that. Okay, great.
Yeah.
Okay. Okay,
Thank
see
you.
you then. Week after 4th. Okay, bye. Bye, everybody.
Thank you. Bye.